Pada-bum. Wow, that gets me going. So, welcome everybody to Physics number 107. Been doing this for 2.5 years now, maybe, because we've missed some days. Anyway, welcome. I'm John Mallinckrodt. I'm your host for the Physics, the nearly weekly Physics. And in this room, we talk in the scientific discourse house. We talk about well-established science for the most part, at a slightly deeper level than you normally hear about science. But we like to stick with that to kind of show a little more of the rigor. It's not as rigorous as it could be, but we try to kind of delve into topics that are interesting and with a little more rigor than is usually seen. The topic today is motivated actually by my good friend Benjamin, who I was discussing the concept of interference and diffraction with recently, and it motivated me to do what hopefully will be a few-part series on diffraction and interference, in particular of slits. Maybe we'll talk about circular aperture diffraction as well, and get into Rayleigh's criteria and diffraction limits and all that. But today, I just want to talk. Today, we're gonna start by talking about a simple situation, a single slit, and that will allow us to introduce a really important tool called phasors. And there, you can set them on stun or whatever you'd like. They won't hurt you. They're just little arrows. But phasors are it's really a cool thing. I think some of you might really appreciate how powerful this idea of phasors in dealing with diffraction and interference is. And that's what we're going to do today. I'll say hi to my friends Shamash and Hero, Andy. Thanks for coming, you guys. Thanks for coming, everybody down in the audience as well. How are you doing today? Shamash, are we on?
We are on. Got you early today, and the show is already on YouTube. You can see the link.
Okay, good. And you put the link, right? So we're streaming simultaneously to YouTube. You can watch there if you'd prefer. Thank you, Shamash, for doing that, as always.
Thanks to you, my friend.
Yeah. And good to see you, Andy. Andy just got back from Fiji and doing some scuba diving at the Cousteau Resort near Savu Savu. I need to get those pictures. Did you send me those rainbow pictures yet, Andy? He may be tied up. If he is, somebody call the cops. Let's get him untied. Okay, well, we'll just move on. If anybody'd like to come up on stage and hang out while we talk, there's going to be. I'll just say right at the start there. If you are paying close attention today, there are lots of questions that should occur to you. I'm going to gloss over some things. I'll be happy to say a few words about them, but there's lots of opportunities for you to say, hey, wait a minute, what are you doing here? Because we do make lots of approximations in this. Those approximations are very well justified. For the most part, they're not perfect, but they're very well justified. But I'm not even going to mention a lot of them. I'll mention maybe some of them in the process, but it'll be a fun test for you to find things to ask questions. There'll be plenty of things that you should ask me questions about. And if you'd like to hang out on stage, raise your hand and come on up, and you can do it there. We've been joined by Ben, my good long-term partner, Ben Tristram, from Cambridge, England. How are you doing, Ben?
Very good. How you doing, buddy?
Good.
Cool. Looking forward to it.
Yeah, so this will be kind of a fun one, I think. Maybe we'll launch right in. We've got a pretty good group, unless anybody has chit chat before we get started. Give you 5 seconds to chit chat. Take a sip of coffee, and we'll get started. So if you open the link at the top there, as always, that's the slides for today. Physics number 107. And there's links there to other things. I haven't been very good about updating these slideshows with links to the Clubhouse replay and the YouTube. Sorry, Shamash, I'm going to get around to that here one of these days. I think I'm about 15 weeks behind now. Okay, so there's the title. On the second slide there, just this introduction. what are we talking about? So in this series, and I think it will be a series probably of 3 maybe bites of physics, we're going to explore the patterns formed when, a lot of terminology on this slide, when monochromatic plane waves are normally incident on an opaque barrier with one or more long, narrow slits cut out of it. And then what happened? Those patterns formed by the diffracted, as we call it, light that subsequently falls on a screen behind it. And most importantly, we'll learn about this tool that I mentioned called Phasors. Andy just messaged me saying he's in a class. So he's teaching. Andy's actually teaching right now and hanging out in the bite of physics. How about that? That's remarkable. That's a type A personality to be able to do 2 things like that at the same time. Okay, so what do we mean about this? Monochromatic means the waves have a single wavelength. It refers kind of to the idea of a single color, which would be in the case of light. If you have a single color, that's a single wavelength. A single pure color is a single wavelength of light. But I don't want to limit what I'm saying here to light waves at all. This is waves of any kind. And so when I say monochromatic, I simply mean that we're going to have waves that are coming in with a single wavelength. And they're plane waves, which means that the wave fronts are planes, not spheres or cylinders. A point source of light, for instance, would produce spherical wave fronts emanating out from it. Rays would travel away from the source, and those rays would all be perpendicular to the things we call the wave fronts. If you imagine water waves, the wave itself is extended perpendicularly to the direction of travel. That's an example of a two-dimensional wave. The wave is just a bump on a two-dimensional surface. But wave fronts are pretty easily visualized for water waves. They're just the places where the water is bumped up along some kind of a line. A plane wave and a water wave would actually be just a wave where the wave front is a line. So the wave itself, the bumpy part, isn't spherical, isn't circular basically, or some other shape. It'd be like waves coming to the beach at any normal beach. The waves come in kind of in a linear plane, we would call it, even though it's really not like, well, I'll just say that. We would call them plane waves because the wave fronts are linear. Normally, incident means that the wave, we're going to limit ourselves, so we don't have to do this. It turns out it's easy to relax some of these criteria, but we're going to talk about waves that are coming in perpendicular to the barrier. So the propagation direction is perpendicular, coming straight into the barrier, as shown with the red line in the diagram there. You can see the wave fronts coming, all those wave fronts, which we'll call let's see, I guess I didn't say that. The wave fronts are what we would call surfaces of constant phase. If you think about a water wave, you've got a peak and then a trough and then another peak. The peaks are all places of constant phase separated by one wavelength. The wave goes through one full cycle as it goes from one wave front to the other. But the wave fronts themselves could be troughs. I could draw one of those planes might represent a place where the wave is in effectively a trough. It could be a place where it's halfway between 0 and a maximum, whatever. But it's a place it's a collection of points on this three-dimensional wave in this case that are all at the same place in the cycle. So these waves are normally incident on the barrier. The barrier is opaque. It absorbs incident energy. The slit is an opening through which the wave can pass, a place where the wave energy isn't being absorbed. And the diffraction, and when we talk about diffraction, we really effectively just mean wave alteration. By selective blockage, the wave form will be altered but due to the fact that part of it is not allowed to pass into the region behind the slit, and that's what we're interested in exploring. So let me stop there for a second and just see if there's any comments or questions.
If you want to talk about it, but I've always wondered how is it that you can produce this kind of light, like monochromatic, plain, right? Like, isn't it difficult technically to do that? Is there an easy way?
Yeah, well, there is an easy way these days, but it's a really good question. The monochromatic light, at least, is very easy to produce with a laser. That's what a laser is just completely a pro at doing. So if we have a standard kind of helium neon laser, it produces light at 632 nanometers wavelength. That's in the red region of the light. So a really typical kind of laboratory laser used by students is a helium neon laser. They're cheap and they produce very monochromatic light. Interestingly, as we'll see later on, the laser beam is really tiny, right? It doesn't have much extent to the sides of the beam. It's tightly focused, but we'll actually use laser beams to produce the light, this monochromatic plane waves coming into this barrier. Because in fact, all we really need is a couple of millimeters of wave falling on a slit that's even smaller than a couple of millimeters to produce this effect. So while I'm talking, this is one of the things that I was talking about at the beginning. It's a question that's exactly the kind of question I was suggesting. I'm being a little bit, I'm glossing over the fact that the actual wave I'm going to talk about might only be a couple of millimeters across as it comes in, but that's okay because the slit itself is much tinier even than that. So I hope that all of that helps a little. Let's move on to the next slide where I show some diffraction. This is diffraction of water waves in a device called a ripple tank, which is kind of a demonstration laboratory type thing that students will use in physics class. And there's a bar that moves back and forth at the bottom. There's 3 different pictures here for different slit sizes, basically. But there are water waves coming up from below, heading toward the top of each of these pictures that are plane waves. The wave fronts are straight lines, and then they run into a barrier that has a gap in the middle. And you can see in the picture at the far left, the gap is pretty large, pretty wide. The gap is smaller in the middle picture and smaller yet in the last picture. And so this is just to illustrate some effects of diffraction. You can see in the picture at the far left that what kind of happens on the far side of the slit is, well, you kind of still have the same waves basically traveling on as they did before, but there are these little circular kind of lower amplitude waves spreading out now to the left and right. So you still kind of have that plane wave character in the middle, but then this diffracted circular edge around the side. So that's one effect of diffraction, is that waves bend around corners like that. Let's go to the far right first. In the far right, the slit is much narrower. I should have noted that on the far left, that slit is much wider than the distance between the waves, the wave length, the actual distance from crest to crest. So it's letting it actually, the size of the slit is large compared to the wavelength. In the picture at far right, the slit is relatively small, not much smaller, but it's smaller than the wavelength. And you'll notice that what the waves look like in the region beyond the slit is essentially that it makes it look like the slit is just simply a point source of waves. Waves simply spread out circularly from that as if it were just a point source of waves. Something that really shows the transition from that point source like behavior on the right to the wide gap behavior on the left. Here's a slit that's a little bigger than the wavelength, but still kind of on the order. It's not large compared to the wavelength. It's not small compared to the wavelength. It's a little bigger than the wavelength. And you'll notice a weird effect in the region beyond. You have kind of strong waves, circular arcs at least of waves spreading out, heading in the same direction that they originally were. But then there's kind of on each side of that, there's kind of a region where you don't see any waves at all. And then you see kind of weak waves also in a circular pattern. And then there's another place where those waves disappear. So it's a really interesting pattern. And that, in fact, is the pattern that we're going to be looking at. We're interested in particular kind of understanding. And I'll just call your attention to one other feature of this that we won't talk about specifically. But notice that if you, in that middle picture, if you extend the white regions, let's say, in the wave that goes straight through, there's kind of dark and light regions. If you extend either the light or the dark regions around, you'll notice that they match up with the opposite. In the little wings, if you extend a dark region around, it will become a light region in the wing next to it. And a light region in the main central pattern will extend around to a dark region. So there's a what we would call a 180 degree or half cycle or half period phase difference between the waves in the central one and the waves on the side. I'm actually not going to explain that or talk about that, but it's an interesting feature to notice as well. So let me stop there. Oh, and I put a link to the source of those, not for any particular reason, but there are lots of other good things in that source. Any comments or questions on that? Let me invite Sydney up here if he hasn't been invited.
Hey,
Welcome, Sydney.
hey, no, I think it's interesting that you're talking about that. I was watching a video the other day and it was like explaining why holograms work. And it was literally saying like it's because of that phase detection or like that phase aspect of it. And
Mm-hmm.
like essentially like what they do is they're using a reference beam of laser light and then
Mm-hmm.
they're using a beam of laser light that's capturing the scene, and they're kind of embedding it on like a kind of a glass like negative, and the glass negative is just storing all that interfered and diffracted light, but it
Yeah.
has that phase information with it because of the reference beam. And then so in order to read it back, all you have to do is aim the reference beam back at the negative, and then you see your holographed image, like the entire image from all sides or whatever. And it's because of that like reference beam and how it locks in or records the phase, because that's what you need in order to kind of capture a hologram. Is you not only need like the wavelength amplitude, but you need the phase that the wave is actually on at any given moment of interference.
Yeah, that's exactly right. It's good description. I should probably do a hologram thing sometime. But you're right. It's what you do with a hologram is you have laser light shining on a scene that is reflected off that scene, and then that reflected light interferes with the reference beam itself, creating an exposure pattern in the hologram film that captures the places where the interference is in phase, making a lot of exposure of the film, and places where it's out of phase, where essentially the film is not exposed because there's no amplitude there. And then you reconstruct it by shining that same light on the hologram, which ends up which produces the visual effect in what you see on the far side, or depending on what kind of hologram it is, to reproduce the original scene in full 3D, right? That's the interesting thing, is you can move your eye around and see things. Anyway, yeah, so it's very closely related. It's all of these things are about I'm calling this diffraction. Sometimes people, when talking about multiple slits, they'll talk about interference rather than diffraction. All of these things are ultimately about interference of different waves with different phases, and it is the phases that are absolutely central. So that's, yeah, it's a good example. Anything else? Let's move on then to slide 4. So the approach we're going to take in dealing with diffraction is to consider the unblocked portion of the wave as a collection of point sources that are distributed across the unblocked portion of the incident wave. And then we'll add up their contributions at points on the screen. Hopefully you can already see how this kind of works. If that aperture were very narrow, then essentially you just kind of have a point source producing circular waves or spherical waves like we saw in the middle or in the far right picture in the previous slide. But we're going to consider the light beyond the slit, and in particular on the screen over there at the far right, to just be what you get when you add up all the contributions from those individual sources. And I've shown the slit width there, A. I've shown two coordinates, one coordinate y, which I've just arbitrarily started from the top. So as at the top of the slit, y is 0. In the middle of the slit, y is a over 2. And at the bottom of the slit, y is a. But it's a coordinate that locates your position in the slit. If the slit width is 5 millimeters and y is 2 millimeters, then you haven't quite gotten to the middle of the slit yet, right? And then there's another coordinate I'm showing there called z, which is going to be the distance upward. That's all, both of those are arbitrary choices. I could have chosen anything. I'm choosing z to be the distance upward from the midpoint of the apparatus. There's a line that bisects the slit. That line falls on the screen, which, by the way, I didn't mention. Of course, I'm orienting the screen parallel to the barrier. The barrier and the screen will not be at an angle to each other. That's an arbitrary choice, too, and we could work out the details if it weren't, but there's no point in overly complicating it. So the screen is parallel to the barrier, and z is just the distance from the midpoint of the screen, which is determined by the midpoint of the aperture, upward. And so we'll talk about how the pattern of light or the wave amplitude depends on that coordinate z. Okay, ready to move on to the next slide. On the next slide, so let's think then about how will we find the intensity at this specific point. I just chose an arbitrary point P on the screen, and I'm showing you lots of things on this slide just to kind of make several points. Number one, I've drawn a line from the midpoint of the slit to the point P, and I'm showing the angle theta that line makes with the line straight from the midpoint of the slit to the midpoint of the screen, the place where I'm measuring z from. That angle theta then is formed between that distance from the midpoint of the slit to the point P and the distance d. I'm showing here also the distance d, how far it is to the screen from the barrier, from the slit, if you want. And I'll say just this one thing about D. I'm not gonna spend much time worrying about what D is, other than I want D to be very large compared to the slit aperture. Typically, the slit aperture will be a millimeter or less. I want D to be a meter, 1,000 times the size of the aperture, or at least 10 centimeters, 100 times the aperture size. I want D to be so large that each of those little infinitesimal sources that I've divided the slit up into is the same distance from point P. notice that I've got a little dotted line there where I say change of scale. To the left of that, I'm looking with a microscope at the slit itself. And all of those lines going up at an angle are heading for point P. But it's so far to point P that they look parallel. And it's important for me to be able to treat them as essentially parallel. So we're looking on the left side of this diagram, we're looking at a microscopic view of the light or the wave coming in, the aperture, all of the little sources that I talked about before that are now contributing light to the point P along the path to P. And all of those paths are basically parallel because it's so far to P. On the right side of that little dotted line, I zoom way out so that one line that's going to P is actually all of those lines from the sources. It's just that now I'm at such a big scale that I can't see that there's a whole bunch of contributions on their way to P. Does that make sense? Any comments or questions on that? Really important to kind of understand that.
So we will, sorry, go ahead.
Go ahead.
We will only consider cases where theta is a very small angle here. So because the light could be scattered on the entire screen, and so you could have 10 degrees, 20 degrees, right?
Yeah, that's a good point. We don't really have to consider only cases where theta is small, but I am going to consider cases where theta is small just to make the math easier. If theta isn't small, then well, I should go through. Maybe I didn't quite finish this slide yet, but you're referring, of course, to the equation at the bottom. So let me talk about that a little bit. Then I'll get back to the small theta thing. So all of the sources in the slit are producing contributions in phase because the wave coming in is monochromatic and a plane and normal coming in. So that means that when a wave crest hits the aperture, every single one of those little secondary sources, if you want, is now producing itself a maximum, a wave maximum that will then scatter out, propagate out from that place. And as it shows in the diagram, if the source at the top of the slit is producing a I shouldn't say that. I should say if. I should have just said the source. The source at the top of the slit produces a contribution that will have some phase when it gets to point P. A source below it will be out of phase because the contribution from that slit has to travel a little further to get to point P. So the contribution that's getting to point P is from a slightly earlier time when the wave at its source was at a different phase of the wave. And the thing that determines that amount of out of phaseness is that extra distance that's shown in the orange region there. Except for that extra distance in the orange region, all of the distance to the path is the same. So I can just kind of think about those, the place, the orange place. And in subsequent slides, I'll really concentrate on that orange part. And then, as I say, if you think about just a specific place, y, as y gets bigger, the out of phase that delta x, the extra path distance in the orange, which I'm calling delta x, which is a function of y, gets bigger and bigger. It gets bigger linearly as y. If you double y, you will double the extra distance. So delta x is proportional to y, and in fact, delta x is simply y times the sine of that angle theta. If you know your trig, you can see why that is. But for small angles, the sine of theta is basically the same as tangent of theta. I'm just going to say that. If you know your trig, you understand why that is, or at least you understand that is. And then you also understand that the tangent of that angle theta is the coordinate z divided by the distance d from the aperture to the slit. So the important thing about that is that the extra distance traveled is equal to the y coordinate. The bigger the y coordinate, the bigger the extra distance traveled, times that fraction z over d, which just basically tells you that angle theta. D doesn't change, but as z gets bigger, the angle gets bigger. So what was I saying? Okay, so we're going to limit ourselves to small theta only because I just want to be able to use the delta x equals y times z over d. If I was willing to continue to have sines of thetas and tangents of thetas in there, I could easily relax that. It just makes life simpler. And it is a fact that, for instance, when I shine a laser beam on a 0.5 millimeter slit, let's say a 1/10 of a millimeter slit, and then look at the pattern on a screen that's a meter away, the pattern is confined to a few centimeters. So it is really the case that in all practical situations like this, when we're dealing with light especially, those angles remain 1 or 2 degrees, 3 degrees, maybe 5 degrees at most. They are very small angles. So thanks, Shamash, for that question. It made me at least understand that I hadn't even begun to finish this slide yet. Any more comments after that? Did that help?
Sure, I just
Okay.
make sure that we're on the same page. Yeah.
Yeah, no, good. Thanks for that. All right. Well, let's move on then to slide 6. On slide 6, I'm just showing, well, so how do we find the intensity at the midpoint? That's pretty simple, right? Because now I've just shown you a little zoomed in on the slit itself. At the midpoint of the screen, all of the contributions from the little sources in the aperture itself are going to contribute in phase. They all travel the same distance. They were all in phase at the beginning. They're all going to be in phase when they get to the midpoint. And we represent that. This is our first introduction to phasors. The little black arrows, over on the right are phasors. Each one of those represents the contribution from one of the sources. And in this case, because all of the contributions are in phase, I can find the resulting amplitude at the midpoint by simply taking all of the amplitudes from the contributions and just adding them like vectors, just saying, well, how much total do I have? And when I add up all those vectors, I get the total length of all those vectors is shown by the red arrow. And the resulting amplitude is shown by the blue arrow. In this particular case, you'll see this changing in subsequent slides, but in this particular case, the total length of all those arrows is the same thing as the resulting amplitude, which I show in blue. If I want to know what the amplitude of the wave is at the midpoint, the blue line is that's the thing you want to look at. The red line simply represents the length of all those vectors. If I just add up all the lengths of all those vectors, that's the red line. In this particular case, the red line and the blue line are the same because all the vectors are in the same direction. So we get a fairly healthy wave at the midpoint because there's no phase cancellation, which is what I'm going to show you on the next slide. Any comments on that? I think maybe let me just belay comment. Let's just go to the next slide and then I'll take comments on or questions on both. So what if for instance, what if I want to find the intensity at a place where that extra path length at the bottom, the out of phaseness of the bottom source is a half of a wavelength. If that extra distance a times the quantity z over d, if that distance is half a wavelength, just looking at the diagram at the right, if that longest extra path distance, the one at the bottom, if that thing is half a wavelength, then that final source at the bottom will be producing a contribution at the point P that is exactly out of phase, 1/2 cycle different than the source at the top. When there's a peak from the top, there'll be a trough from the bottom, and vice versa, because they're exactly 1/2 cycle, 1/2 wavelength. And so now what I have is a situation where the phasors get progressively out of phase with each other until when I get to the bottom one, I'm exactly out of phase. And we represent that by taking all those little phasors, the little black arrows, and tilting them a little bit. Each one is a little more tilted, a little tilted away than the previous one, until the final one is pointing in the opposite direction as the first one. And the resulting amplitude is just what I get considering those as what we call a vector sum. If I draw the blue arrow from the place where I drew the first phasor to the tip of the arrow of the last phasor. And now you can see that the resulting amplitude, the blue arrow, is shorter than the sum of the lengths, which I'm still showing in red. The length of that red thing is still the same as it was on the previous slide, but now it's curved into a circle, giving me a shorter resulting amplitude. So there's going to be light, there's going to be wave amplitude at this point P, but it's going to be less bright, it's going to have less amplitude, less intensity than it did at the center, because there's some phase cancellation going on. The sources aren't all pumping in unison anymore. They're kind of canceling, they partially cancel each other out. This is a concept that takes a little getting used to, and especially you might say, well, why does it work there? How do you get to just take those phasors and angle them off like that? A lot of reasons you should be skeptical of this, because it's really just a graphical way of doing some complex math, basically. I'll leave it at that to see if there's any comments or questions on this particular slide. And maybe you can kind of see where we're going to go with this. The further, so remember Z was the coordinate on the screen away from the center. As Z gets bigger and bigger, as the point P that I'm talking about on the screen, as that point P moves further away from the center of the pattern, there's going to be more and more phase cancellation. I'm going to take these phasors, I'm going to put them, they're going to curve around like this into a circle. The length, the red thing, is going to always have the same length, but it's going to curl up into a circle. It's going to get smaller and smaller circle, and the resulting vector then is, you just simply determine the resulting vector like I have here. So maybe with that in mind, look at slide 8, where I'm now looking at a place. I'm showing you the same diagram, sorry about that. But suppose that extra length at the bottom, the extra length at the bottom, suppose that was one wavelength, AZ over D. Suppose that was one wavelength. Now you have a situation where the source at the bottom is producing a contribution that's exactly in phase with the source at the top. It comes from a wave that's a one cycle later or earlier, depending on how you want to think about it. But they're both in phase. The top source and the bottom source are in phase. In between, of course, you have all possible phases. At the midpoint of the aperture, that extra path length is a half of a wavelength. So you've still got the case where the contribution from the middle, I should say, in this situation, the contribution from the middle of the aperture exactly cancels the contribution from the top of the aperture. And the source slightly below that, but slightly below the midpoint, will be exactly out of phase with a point slightly below the top, and so on, all the way down. For every source in the upper half of the aperture, there's a source in the lower half of the aperture that exactly cancels its contribution. And what that looks like when you draw the phasor diagram is you have a set of phasors now that start in some direction and end in the same direction, having gone through all possible directions in between. You still have the red line, the same length as it always is. It's the sum of the lengths of all the phasors. But the resulting phasor is zero. There's no net amplitude because when you when you add that last phasor in, you come back exactly to where you started from. If you draw a blue line from the starting point to the ending point, because the starting point and the ending point are the same, the blue line has zero length. You have a resulting amplitude of zero. Okay, I'm really going to stop there for just a few moments, see if anybody has a comment.
So these phasors are supposed to be not light marks, because like at the beginning we only saw a straight line when the aperture was too big, and
Uh,
we considered those small micro sources, and then the contribution of each one, and then you add them, and you get the line or the light spot. Fantastic. But here they mean something else.
so I'm not sure. Let's do a quick review. Let's go back to slide 6 and
Yeah.
just notice that in that case, all of the contributions are in phase. That means if I had a suppose it was a water wave. I had a 1 centimeter high water wave, and then I added another 1 centimeter water wave in the same phase. Then I'd end up with a 2 centimeter water wave. And if I had 5 of them, I'd have a 5 centimeter water wave. And that's really all we're saying. I think in this case, the phasor thing isn't really important. You're just saying, well, I have 10 contributions. Each one's giving me a 1 centimeter wave, and they're all in phase. I now have a 10 centimeter wave, right? So at least in that particular, in slide 6, it's all pretty clear. We just simply, if we've got 100 sources, I'll have an amplitude that's 100 times the amplitude of any one of the sources. The thing that's a little harder to understand is how it is that you can get away with saying, as I'm saying here, that when they're not all in phase, you can really get the resulting amplitude simply by adding up these little vectors, as I've done here, putting them tail to tip, 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 until I run out of contributions, showing their phase by an angle kind of clockwise, right? An increasing angle clockwise. That part it shouldn't be immediately obvious that you do that, that works. That comes from thinking about the trigonometry of adding sources that have different phases. But it does turn out that you can show that the result of adding all of those contributions at different phases is indeed done is indeed given by this geometric construction of just taking the individual phasors, having each one tilt off at the same angle relative to the previous one, and then adding them up. And you can see that the fact that the angle increases linearly as the sources are getting further away means that you'll get this circular arc kind of thing. It only becomes a better circular arc as I divide the aperture up into more and more sources. And of course, ultimately, in the sense of calculus, I'm going to have an infinite number of infinitesimal sources, all of which add up, in the lengths of which all add up always to the same thing. But because of their out of phaseness, you get the cancellation. You notice that in the case on slide 7, the final contribution exactly cancels the first. I'm drawing it way over there on the right compared to the first one, which is over on the left. But in terms of contribution to the length of the resultant, I could just take them away. They don't matter because they exactly cancel each other. And then
Just
finally on slide 8, when you've gone so far that the final one is in the same direction, that circle, that circular arc has now for the first time become a complete circle. Yeah, go ahead.
I just failed to see what that vector denotes. That's it. So its angle and its length. I guess the length is uniform, so it doesn't matter because we're just making arbitrary divisions in the fictional micro sources we have. But the angle of it is exactly that extra length of.
Yeah, it represents it, right? It's the extra length divided by the wavelength in cycles, right? So if the extra length is a quarter of a wavelength, then you know that you're a quarter of a cycle out of phase.
So you would be 90 degrees away, so it would be a
Right,
horizontal arrow. And
right.
then 180 would be a vertical arrow, but pointing downwards.
That's right.
Okay.
Yeah, and I think you're exactly right. I mean, I think it should be pretty clear why I'm drawing all the phasors the same length, because all these little, I'm going to divide it up into uniform sized microscopic sources. So each one contributes the same amount. That's why the lengths are the same. The only thing that's a little bit, that's not just a little bit, I think it takes a lot of thinking of, it actually takes working through the math in trigonometry to see why this geometric construction gives you the right answer when you just take those phase differences and tilt the arrows and then add them. That's not obvious at all. But it does turn out to be equivalent to simply doing the math and adding out of phase contributions. It's to do it. Usually, we represent the contributions in the complex plane, and then these little phasors really are kind of things that have real and imaginary parts in mathematically. That's the way we end up really doing the math. So I'm kind of just telling you at some level, your discomfort here, Shamash, is correct. You should be uncomfortable because I haven't shown you why this geometric construction really does work, but I could, and
I
that's the
see.
way I'll
No,
leave
no,
it.
no. I see it. When you said complex plane, I kind of imagine now where this is coming from.
Uh huh.
Am I right in saying that on slide 8, in that case, we will see nothing on the screen? Do I get that
That
right?
That's right. So at the point where this is true, there will be a wave with zero amplitude, and therefore, if it's light, it will not be lit up. If it's waves, like if you refer back to that, what is it, slide 3, the middle frame, there's that one angle where you see no waves. Now, that's the angle we're talking about here. That's the angle where the contribution from one side of the slit is exactly the same phase as the contribution from the other side of the slit. And you have cancellation, a perfect cancellation because of the fact that you've gone through one full cycle. Yeah, those are all good things to be puzzled about and so on. But anyway, we're going to use this same idea. So you're if you have discomfort with the idea that this works, that's fair enough. You can continue to think about that. We're going to use these phasor ideas throughout this series. So I want to at least make them sound plausible and then show you the results and then convince you with the fact that the results you get map onto what we actually see when we do the experiment, and we'll do that too. So if I move on to slide 9, I'm now doing there's 7 different examples here. The first 3 of which we've already seen. So at z equals 0, that's the center point on the screen, you've got that maximum amplitude. And I'm calling it R naught. R naught the amplitude of the wave is equal to the sum of the lengths of the phasors, the red arrow right next to it, just like we've already seen. So that's what we see in terms of amplitude at z equals 0. Going slightly to the right, you see the half circle thing that we've already talked about. That's what happens when z is one half of lambda d over a. I was in the past I was talking about, for instance, if you look at slide 8 again, this is what happens when a times z over d is equal to the wavelength. Now I'm talking about it in terms of what happens at z. What I really want to know is what happens at a coordinate z on the screen. Remember, z is the distance on the screen from the midpoint. So if I solve that equation for z, I get z is equal to, for slide 8, I get z is equal to the wavelength times d divided by a. So so you'll see I'm doing all of these in terms of the wavelength times d divided by a. So that semicircle, you see the semicircle again, that's when z is half of lambda d over a. And I'm showing you one other thing there. Because the length of the red line is equal to r naught. Look at the z equals 0 thing. You'll see that the length of the red line is equal to r naught, but now it's curved into a semicircle. And because the resulting vector is the diameter of that semicircle, I can do a little math and show that in that case where it's just the semicircle that we talked about on slide 7, the resulting vector is 2 over pi times the thing I called r naught. Remember, r naught was the amplitude in the center. It's equal to the length of the red line, which is always the same. The red line always has the same length. And because now that red line is a half of a circle, you can show that its diameter is 2 over pi times that length, which is r naught. So I'm showing you the amplitude being, what's that, about 3/7 or something of what it was before. Okay, and then I'm showing you once again what happens when the extra length is one wavelength, when z is equal to 1 times lambda d over a. That red line, which always has the same length, is curled into a circle, coming back on itself. The resulting vector has 0 length. There's no amplitude in that case. But on this slide, I continue. I go to the case when I go out to a z that's now 3/2 times lambda d over a, or twice lambda d over a, or 5/2 lambda d over a, or 3 times lambda d over a. Well, what happens? And you start to see a nice pattern. The nice thing about this is you'll start to forget that you didn't really understand how the phasor thing worked, and you'll just see how simple it is to kind of work this out. When I go to a place where that final extra path length is 3/2 of a wavelength, I didn't show you a picture for this, but if the extra path from the bottom source is 3/2 of a wavelength, you end up at point z on the screen that's 3/2 lambda d over a. And in that case, the red line, which is always the same length, has to get curled into 1.5 circles. So it goes all the way around and then halfway around again. And you see that the circle is getting smaller, right? Because the red is the same length all the time, but now it's got to go around 1.5 times. And my resulting vector now is the diameter of that circle. The circle has a circumference that is 2/3 the length of the red line, because it goes around another half a time. So 2/3 of it is what's required to get around once. And then I can take that circumference and divide by pi to get the length of the resulting vector. So at this point, the length of the resulting vector is 2/3 pi times what it was at z equals 0. And I invite you right now to just think about, I'm not showing you all the intermediate cases, but I hope you can see that between z equals 0 and z equal 1/2 lambda d over a, the resulting vector is just progressively getting smaller and smaller and smaller. It gets to what it is at z equal 1/2 lambda d over a, and then it continues to get smaller. So the circle is tightening up, and the final vector is getting closer to the original vector. So it's just getting smaller and smaller and smaller until it finally is 0 when z is equal to lambda d over a. And then it starts to come back again, so that I get something in that next picture, the 3/2. I'll just refer to it as 3/2. I have another, I get some amplitude. But then it tightens up again, because when I go to z equal 2 lambda d over a, the red line has to get curled into 2 full cycles around a small circle. It's still the same total length. The circumference of that circle is now half of what it was for the first circle, because now the red line has to get wrapped around it twice. But once again, I have 0 resulting vector. And then I show you one more. I'll just go one more. If I wrap it around 2.5 times, which is what happens when z is 5/2 lambda, when I'm on a point on the screen where it's 5/2 lambda d over a, now I have to wrap the red line around 2.5 times. Once again, I now have a little resultant vector. You can work out what that length is, and you start to see a pattern. Now it's 2/5 pi times r naught. And then I wrap it around 3 full times and I get 0 again. And I hope you can see that if I continued this along the top line there, I'm going to get 2/7 pi, then I'm going to get 2/9 pi, 2/11 pi, 2/13 pi. It just continues of that same thing. And along the bottom line, I'm going to get 0, 0, 0, 0, 0. I wrap it up into a circle, wrap it up into 2 circles, wrap it up into 3 circles, 4 circles, 5 circles. So as I go further away from the center point on the screen, I come down from a very big maximum in the center to 0, and then it comes back up to a maximum of some kind, and then it goes to 0, and then it comes back up to a slightly smaller maximum, and then to 0, and continuing on and on and on. Okay. Oh boy, we have lots of questions here. Let me get these people up on stage. Let me get Joe up, get Benjamin up. Hi, Joe. Question? Comment?
Oh, I was kind of interesting about the orientation math you had to do, the geometry math or normalization math. What were some of those that you found? Why didn't you go into it? Why was it a kick the can, let's do it not today?
Yeah, we can talk about the. I mean, it's if you have some facility with trigonometry, and even better if you know things like e to the I theta is sine theta or cosine theta plus I sine theta. Little complex math. The phasor diagrams can be understood much easier if you understand adding sine waves out of phase using that complex notation. But it ends up geometrically being exactly the same thing that we're doing here with the phasors.
So I had a thought hypothesis that I want to experiment out. So if I have 2 objects, you have a single light source. All right. You have 2 objects moving at different speeds. Then you can presume at some point they may see different colors or spectrums or frequency of
Doppler
the light.
shift.
Yep.
Hmm.
Okay, so now you do it the opposite way and you say you have two light sources, and one is stationary and one is traveling. How do I play that out in my head?
So I'm not sure where you're going. Are you trying to appeal to the relativistic idea that everybody sees light travel at the same speed, or
Yes, that everyone sees light traveling at the same speed. However, when the objects of light themselves are moving, they are on different scales.
well, this would all be interesting stuff. Let's if you want to explore this further, why don't we finish up the
Absolutely.
presentation and we can talk about that because it's not really related to this because we're not talking about moving sources or observers at this point. But I'm happy. I love talking about that stuff, so we can talk about it
Yeah, if you
later.
could just, as a kind of like you didn't want to do the geometry math or whatever before, talking about as a tangential, that might be something if it was moving.
Hmm.
As you kind of
Yeah.
go through the remainder of this, that would be very fascinating to hear.
Well, I think we'll get to that. If you have moving sources, all that's really, as far as we're concerned, you could have moving sources that would change the wavelength of the light that we're using, and that's fine. You can have different wavelength light. If you want the screen to be moving relative to the aperture, or the light source and the aperture both moving with respect to them, you're just talking about relativistic effects now that will effectively just kind of change the wavelength. Other than that, the math will be the same, unless you're changing the orientation of the slit, taking the barrier and moving it, changing it at an angle, moving the aperture, moving the changing the orientation of the screen. Those are things that will change the actual math, but in ways that we can also
That's an
talk
interesting
about.
one.
Yeah.
Vectorize the aperture.
Right. I mean, it's going to do the kinds of things you'd expect, right? When light falls on a falls at normal incidence on a surface, it's pretty intense, and when that surface is at some angle, the light's getting spread over more area, so it's less intense. That the area delivered, the energy delivered to a given area is different. Anyway, let's delay that for a moment. We can get back to that if you want in the discussion. I've got Benjamin up here too. Benjamin, did you want to comment on something, or have you just got data on your mind?
Seems to be a song, doesn't it?
I'll bring some data pretty soon.
Oh, okay. I've heard that before.
Okay.
I've been thinking about this. I think the challenge is to explain these patterns without
Math.
getting into getting in committing to a wave phenomena.
Mm-hmm. That's a
And
challenge. I will say that is a challenge.
right, that's the challenge. And I think that the key to understand a photon is that it's a interaction between a magnetic field and an electrical field. Certainly has some oscillatory properties, but I don't think it's a disturbance in a wave, in a field, the way a wave is. I
Well,
think
this sounds like, yeah, this sounds
it is
like
its own field.
this is another thing I mean, really should talk about this because I haven't made the claim yet, but I will now for your benefit that the when an electron beam is sent at a small aperture, you get exactly the same pattern of electron detections behind that screen as you do as we're talking about here. You will get exactly the same pattern that we talk about, and at least in the quantum mechanical model, that's explained by saying that the electron is traveling as a wave. It's not a particle. It's not something that goes in a definite position. It's a wave, and part of the wave is blocked by the barrier, but parts get through, and parts of that wave then get through the aperture, interfere on the screen, and the probability of detecting the actual electron itself, of having a particle detection, the probability is determined exactly the same way that we're talking about here in terms of the intensity of light. And light
I
does the
think
same thing because light is
another key of
photons and it does
another key to
that too.
understanding this for me, and it may be different for you, but there's this claim that light takes all possible paths. I don't think that that's part of the way I would understand this. I think that's the way Feynman taught students to calculate it, and there may be an error in that. In other words, not everything that works is science. Is the way that not
Oh,
every
that's interesting.
mathematical solution is the description of the way the world works.
So I think that's an interesting statement. Not everything that works is science, because I kind of think that's the only thing that's science, right? Science comes up with an idea, and if the idea works, you stick with it. That's really because you can't do anything else.
Well, let's take the calculation of the planets as an example, right? There is a way to predict where the planets will be using epicycles or some weird
Mm-hmm.
thing, and eventually you can math the location of the planets accurately. It's very complicated, and I think you might say, well, the math works, therefore that's what the planets must be doing. They must be doing these little
Oh, but science
wiggly
never says
piggly
that. I mean, if
epicycles.
scientists ever say that, they're slipping up, right? Because we don't know what really happens. I mean, we don't know what's really going on. All we know is what we can measure.
Yeah, but I think it's well within reason to say that a heliocentric calculation of where the planets will be is closer
Oh, well, it's not
ontologically
just
to the
closer. I
way
mean,
they really are than
so
is
the
the epicycle
epicycle
math.
thing, the epicycle thing is wrong because it makes predictions about distances to things that just aren't so. I mean, we now know those distances, and they're just not so.
Right. So we can maybe asymptotically get closer, our models can asymptotically get closer to the reality. At least that would be a hope, a reasonable hope.
This is a great
And
discussion, but let's do delay it for a couple more slides. I mean, I would
oh yeah,
definitely talk about this
absolutely.
a little more. So let me just finish this up because we're basically right there. If you once again take a look at slide 9, you kind of see the pattern that we've got. Every time we go out on the screen by 1 times lambda d over a, we get to a place where there's no amplitude of the wave. And in between those, there are little local maximums that are getting smaller and smaller as we get further and further out. So I show that on slide 10. If you just take the only thing we need to know the only additional thing you need to know to finish this off is that the intensity of a wave is proportional to the square of its amplitude. So we can take those amplitudes that we're determining and square them to get the pattern on the screen itself. So what I'm showing here in the graph is this is what the pattern looks like. I'm showing the position on the screen on the horizontal axis. There's the central point, which I call 0. And then I'm ticking off units on the screen in terms of the ratio of z, the distance away from the center, to that lambda d over a thing, right? When z is equal to lambda d over a, then that's the 1 or the -1 if you want. When z is equal to 2 lambda d over a, that's 2, etc. And then you've got the half in between, the half, the 3 halves, the 5 halves, etc. in between. So we can take those amplitudes and square them. If I square the r naught, the amplitude in the center, I get I max. If I square the 2 over 3 pi r naught, I get 4 over 9 pi. I should have, sorry, 4 over 9 pi squared. There should be a pi squared there. Oh, damn, I screwed it up. I screwed up the numbers too. I realized that whole, yeah. Oh, that graph is really screwed up. Anyway, if I square it, I get 4 over 9 pi squared, not 4 over 9 pi, times r naught squared. R naught squared is I max, basically. So I'm just showing you what the successive things look like. Now, all of the numbers, so my formulas are all wrong because they should all be pi squareds. And my numbers, I was wondering why the numbers were as big as they were because I knew they were smaller than that. That 14% should be more like 4%. And the 5.1% should be more like, 1.8 or 1.9. You have to divide each one of those by an additional pi. So I'm showing them too big. I'm mathing them as too big, but the basic idea is still true. The successive maxima get smaller and smaller and are separated by zeros every time z is equal to every time z is equal to an integer multiple of lambda d over a, except note at the center. The central, and one of the interesting things about this pattern is that the central maximum is both much brighter and twice as wide. That's really important. Twice as wide as all of the secondary maxima. The secondary maxima go from, 1 to 2 or 2 to 3 or 3 to 4. The central maximum goes from -1 to 1 because there's not a 0 at 0. Every other integer on that axis gives me a place of no intensity. So the result of all this is that the single slit diffraction pattern includes a broad central maximum that's both broad and intense, and then this series of less bright secondary maxima. And there's a video there that talks about the production of this. I haven't watched the video. It had this diagram, which of course is saying exactly the same thing that I've been saying as well, and showing you a photograph of a laser produced single slit diffraction pattern. And I suspect that video would be maybe interesting to watch. It might clear up some of the things that I've been less clear about during the bite here. So I'll just finish. Well, I guess I have two slides yet, but the last content slide is slide 11, where take that result and talk about the effect of wavelength and slit width. Because the zeros occur at integer multiples of the wavelength times d, which is just the distance from the aperture to the screen, not an important thing except that it should be
To
relatively
that
big,
point,
divided
but
by
where
a. That would get, yeah, go ahead.
where you're squaring that, that's kind of where it's interesting. If it was to be moving or other spots moving, it would have another point of reference not and a difference from like an offset.
A different place where the maximum, where the central maximum is. That's what you're saying. Well,
Every one of those places that you go to square, it's the reason why you're doing it is because you're referencing it from its own not itself, its self-referential point when it's not moving. But when you go to move it, it's usually that and a number.
well, I'm not sure what you're saying. I mean, if I were just to move the source toward or away from the slit, for instance, all that would do would be to change the wavelength. It wouldn't the central maximum. If the source is moving perpendicular to the line to the aperture, then of course the central maximum is going to kind of move too. I mean, it becomes a case where now I don't have normally incident waves. Makes things more
Yeah,
complicated. We
yeah,
can
yeah.
we can calculate all that, but you still get the same
Yep.
same. There's going to be a central maximum somewhere. It itself may be moving in that case, but I can still talk about it at any given instant. Anyway, all I wanted to say on this slide was just that over on the left, we're showing the effect of aperture. Aperture is A. So the zeros occur at integer multiples of lambda d over A. And that says that the aperture width, if I make the aperture width smaller, the zeros get further apart. So the smaller the aperture, the wider that central maximum is. And you can see that in the diagram here. It starts, oh, this is a case says the 0.16 nanometers. Oh, that can't be right. I know. Anyway, I didn't look at the units, but the in that diagram at the left, the top line is a wide aperture. Notice it's 0.16. It says nanometers, but I don't think I believe that. I think that should be millimeters. And then the one below that is half the
Nanometer
width.
sounds like the distance between a wavelength.
But if it's nanometers, then the wavelength itself has to be much smaller than even zero point 0.1 nanometers. Wavelengths of light are or hundreds of nanometers. So there's something wrong. It's got to be millimeters, I think. Anyway, I don't understand. The important point is that the aperture is getting smaller and smaller, and the central maximum is getting wider and wider. There's an inverse relationship between the size of the width and the size of that central maximum, and that's the important thing in keeping with the thing we worked out. And then the picture on the right shows the effective wavelength. It shows using a green laser, a 532 nanometer laser, and a 670 nanometer red laser. You can see that the central maximum is slightly larger at 670 nanometers for the same aperture that it would be for 532. And that's because the size of the central maximum is directly proportional to the wavelength. If you make the wavelength larger, the central maximum gets larger. And that's really pretty much it. Let me just quickly finish the summary, and then we can talk about any of these issues. The important thing we've done here is to show that a single slit produces a diffraction pattern with a bright and wide central maximum surrounded by smaller in width and dimmer secondary maxima. In this particular pattern, this twice as wide for the central, much brighter, and the width of the central maximum is directly proportional to the wavelength, inversely proportional to the slit width. And then finally, just to say that this phasor approach we've introduced here is incredibly useful. It's used to determine diffraction patterns in kind of arbitrary situations, and we're going to use it the next couple of weeks to talk about multiple slits and maybe even circular apertures. We'll see where we go from there. So with that, yeah, definitely Joe, Benjamin, anybody else, let's launch into whatever it is you'd like to explore. Or anybody, yeah. Go ahead, Joe.
Well, from my perspective, the tricky things here is to understand particles versus waves.
Mm-hmm.
We can think of light. We can certainly do a good job of calculating light if we understand phase. But the fact that something has a phase doesn't mean it's a wave. For example, an elongated asteroid tumbling through the solar system has a phase. And that doesn't make it a wave just because it has a phase.
Well, what do you mean by having a phase?
Yeah.
What is this UMA?
I think you just broke up, Benjamin. I'm not hearing you.
When I'm going, like, during my adolescence, I had like a crazy phase, and now I have an indifference phase, but I'm not sure this is the same phase we're talking about.
Right, but it has a phase. We could describe its location as a vector.
Phase? I don't know. I just don't understand. Yeah, okay. So just be clear about what you mean by a phase.
In order to describe its location, we would have to first say sort of where its mass centroid is and the vector of its mass centroid. That's be the first vector. And
we have to locate it. That doesn't have anything to do with a phase. I don't know what you mean by phase.
We locate. I understand. First, we locate it, meaning its center of mass.
Uh-huh.
And then we might have a comment about its rotation,
It's
how quickly
orientation. It's rotational orientation. That's not phase. That's just not phase.
it can be described with phase.
Well,
You
you
can
can
use all
use
the
the
same
word.
phase
It's a kind of
mass.
a misuse of the word
Well, you end up with a a
because it's not a
pointer.
number, right? I mean, in three-dimensional space, you need two angles. You need three positional coordinates, and then no, sorry, three angles, right? Three angles and three
Yeah, yeah.
positional coordinates.
But you would need
Which
John,
all
one?
of those to describe the axis of elongation
Right, but
as it
that's not.
tumbles.
That's just not.
hang on,
Unless
hang
you
on,
want to say
Benjamin.
that. Yeah. Go ahead.
If I'm standing up now and I draw an arrow from my feet with in the same direction and then it's pointed towards my head, do I have phase now?
Uh,
If you are frozen and you're tumbling through space,
I'm
the
jumping
angle
on the
from your feet to
trampoline,
your
right?
head.
I can do rotations, I can do whatever. I'm jumping on the trampoline. Do I have phase now?
But you're not a rigid body, so you have lots of phases.
Very
One could
rigid.
describe.
I'm very rigid.
Yeah, it's just
Yeah,
a
just
I
I
like
look,
to
Benjamin. It's
include one of
just
my
I
a
don't
favorite
think phase
phases.
is simple
it's
enough.
just a misuse of the word. I mean, if you want to call it phase, that's fine, but it's not what we're talking about here. You're talking about rotational orientation in space. That's not phase.
It may be part of phase. Don't discount it as part of phase. Hold on, no, I'll give you a great one. One of my favorite phases are electron phasings. So an excitation of electron, very, very atomic, right? What causes them? Sunspots. So you have an orientation of the sun where a solar storm is pointed towards the Earth, at which an EM field is sent on an orientation, and it helps other excitations in phasing of electrons.
I'm not following you, Joe.
Really?
Yeah, I really am not.
Damn it. Anybody else want to translate Joe for the audience?
Well, I would say that the phases of the moon is a pretty common description, and the brightness of the moon is going to oscillate.
The phases of the moon, I think, is a good example of phase because it's one number, right? It's a cycle, and you can say, okay, it's if you call full moon zero phase, then you can describe all of the phases of the moon as an angle, a phase, right?
Right.
But you can't do that with rotational orientation in space. That's not a phase.
Well, let's just stick with the moon then, because the metaphor is not important.
Okay.
Moon has a phase. Obviously, the moon is mostly massive, not wave-like. Um, Particles. When I look at my screen and I see a letter and I think about how infinitesimally small the source of light is that makes up the top right corner of that letter, I'm inclined to think that corner travels straight to my eye, and it doesn't go in some football-shaped, wandering, meandering, infinitely variegated path. It doesn't take all possible paths to my eye. If I put my hands up and occlude part of the screen, it doesn't affect that dot that I'm looking at until I clip over it, etc. So I'm inclined to think that for the most part that dot is passing pretty closely to my eye. Now my iris is an interesting property here because I can capture all the different paths. I can capture photons that travel in a variety of paths as long as they intercept with my iris. And then the lens
You
brings them
talking about your
down to,
retina?
well, the iris is the hole into which the
Oh,
light
okay. All
first
right.
passes, and then it gets into a lens, and then it
Okay. Yeah.
emerges on the retina.
Right.
So the conical acceptance angle for that single point on my phone is more than just the width of the single photon would be. But I still have to imagine a single photon is mostly traveling through a center point. It's
Oh,
not it's not
I
getting.
think I think that's wrong. If you're saying, I mean, that's a weird thing to say that somehow when you use a lens, for instance, if you use a lens to focus the sun's rays and burn a piece of
Sure.
paper or something like that. The light isn't mostly traveling through the center of the lens.
No, no. I think each photon travels in its own space, but what I wouldn't think is that one particular photon would hit the entire lens and that one particular photon would be focused down on my retina. Rather, I think the purpose of a large lens is to catch more photons. But each photon only intercepts a part of the lens which is equivalent to its wavelength.
Well, I mean, I don't know that I have any big disagreement with a lot of what you're saying. I mean, I will point out that if you shine very dim light on a single slit, and you have CCD detector, behind that, a sensitive single photon detecting apparatus of some kind, you'll find that each photon lands at some weird place on the screen, right? I mean, that's just a fact. It doesn't land in the center. It lands at some weird place on the screen, and then you collect more and more, and they all are landing at places that seem completely random. It's only after collecting thousands of photon hits that you notice that there are these lines along which photons never hit, and other
So
lines
here's
along
here's
which
an
they do.
interesting question for you. If you could clone photons, produce the same photon over and over, do you think they would all land in the same spot, or do you think they would land in
I don't
different
I don't know
spots?
what that means exactly to clone photons. I mean, I
If you
think the
gave
best thing we
photons
can
the
do.
same initial conditions before
Well, the
they
best
hit the
thing we
slit.
can do is use a laser to produce photons that have, a single wavelength, pretty much. I mean, it's not a perfectly single wavelength, but that's kind of the best thing we can do. All traveling in the same direction, not exactly the same direction, but pretty good. That's kind of the best thing we can do. And then you shine that laser on a single slit, and
I
you
understand it's the
make it
best we
weak,
can
you
do,
get
but I'm just curious
this
about
kind
the
of thing.
model in your head. Do you think if we could replicate, or let's
Hmm.
just roll time back and take that photon after it hits the screen, roll time
Hmm.
back and run it again?
It's a long walk.
We just roll it back and run it again. Do you think it would do exactly the same thing the second time it went through the
Yeah,
slit?
well, I think you're getting kind of at Roger Penrose's idea about quantum mechanics. I think he might say that there is something that actually, determines where that photon is going to land. I don't know if he would say that or not, but certainly the standard interpretation of quantum mechanics, one that works, one that gives us the right answers, is that no, identical photons would land at different places.
Right. I would say if you believe that, that's where you and I disagree. I
Yeah,
think I
and that's
think
fair. That's completely fair. I think because that's
what
weird, right?
what
That's
is
weird.
that game where you have a
Ooh,
ball
ooh,
and it drops through, wait just a second, Joe. And it drops through a maze and it comes out in one
Plinko.
of several
Pachinko.
buckets. Pachinko, right? Would you imagine that if you introduced the same ball that it would bounce in the same way through the pachinko?
Right. I would imagine that if you really did put a ball into that device with exactly the same position and momentum and all that kind of stuff, that it would fall into the same, final
Right.
thing, whatever they
And
call
and
those
you
things.
think that light is just different than that.
Yeah, I do. I mean,
Yeah.
I think that in fact, I guess I would venture to say this, that if you really could make those balls give them exactly the same momentum, then it would depend a little bit on how big the final containers are, et cetera. They could possibly fall a little differently. But my judgment is based on the fact that these quantum mechanical effects are completely unobservable because of the size of the slots that those balls fall into ultimately, and the size of the balls themselves. If you could make them, if you could really give them exactly the same, if you could really give them exactly the same initial conditions, they would fall into exactly the same thing. Not so much because they would do exactly the same thing, but whatever difference they would have wouldn't be enough to make them fall into something else.
Yeah,
I'll
so
take
in
a.
my mind, a photon going through a slit, I think of it a little bit like a tumbling football. It's a little bit eccentric. If it was spherical, it'd probably have the same, go through the slit the same way every time. But let's assume it's like weirdly shaped, maybe football shaped. Sometimes it slips through and doesn't really disturb too much, and then sometimes it like hits sideways and it
So how
gets a
does
lot
your,
of
that's fair.
diffraction.
How does you,
May I interject a perfect analogy for this? And it was from someone that
Joe,
designs.
I'll be
It's
done in
Benjamin. It's
just
on
a
top of
second.
this.
I'll be done in just a second. What were you saying, John?
well, so I was just going to say, and then we will let Joe
Yeah.
interject. I was just going to say, I don't know how in your model you account for the fact that you get exactly the pattern that my model says you'll get. Right, the quantum mechanical model gives you a very specific prediction, which is what we see.
Yeah, well, let's let Joe talk, but I
Yeah.
would just say that when you put two shapes together, you get certain outcomes are possible and certain outcomes aren't, and then that explains it. But let's
Well,
let
I
Joe.
think
Hi,
you
Joe.
haven't explained it. You've offered a different interpretation, but you don't have a mechanism to
Cool.
actually give a prediction. Go,
Fair
go
enough.
ahead,
All
Joe, and
right.
then we'll get
So
back to
the
you.
light hits the lens, the light goes through the lens, and then it gets the aperture. Can we agree?
Uh, I guess I don't know what you mean. Light goes through. What's the
Through a
situation you're talking
lens,
about?
and then eventually, after it goes through that lens, it'll hit our aperture. Can we agree on that?
What,
As
what
a
are you talking
basic
about? Our
experiment.
eyes? What are
Yep,
we
sure. Let's
in our eyes?
talk. Um, here's where I'm going to take this. You take a lens and you start polishing that lens to take in light from, for like a Hubble telescope. The point is that when they create telescope lenses in the first place, the orientation of the atoms change properties of how light comes into the aperture. And
The
so
orientation of
if
what
like
atoms change the?
uh,
You're talking about
the
changing the orientation of how light comes into.
basically if it hits the lens in the same exact spot, but you
Oh,
change the angle of the lens because of the atomic structure or latticing in the lens, you end up having a variation of acceptance. You have sometimes
I'm not.
scatter and it doesn't go through the lens into a zone of acceptance
I'm not really
just
not
based on
following
that.
your. Yeah, I don't. How does the atomic structure of the lens? Do you need that? Do you really need the lens to do anything other than what a lens does?
Well,
I
the
mean,
atomic structure ends up being how do I put it? It's the degrees of freedom. At some point, the atomic structure then
but it
affects your
sounds to
degrees of
me like
freedom of acceptance.
you're talking about an imperfect lens, a lens that doesn't do exactly what a lens does because of the atomic structure of the material that it's made of. Is that what you're referring to?
Yeah, essentially, it's the boundary layer at which light comes in. It has a diffraction angle.
So this lens then produces an unpredictable output because it doesn't do what lenses do in theory.
Well, it's if the photon hits the lens in the same exact spot, the exact same spot. I don't know what's going off
Well,
in power.
but that's you
But
understand
you
that
change the
there's
angle
no
of the lens,
that's
you
not
have
even
a
a
change
thing.
in probability.
I mean, first of all, photons don't hit lenses at, I mean, in the model, right? I mean, you've got some different physical model here. In the model, in the current model that we use successfully, photons are only things when you detect them, when they deposit their energy in something and cease to be photons. So you can't talk about a photon hitting a lens and then going through it. If the photon hits at a certain spot, that's because it deposited all of its energy there.
So then there's sometimes that if you change the angle, it may deposit its energy there or it may not.
Change the angle of what?
Change the angle of the lens at which the photon hits.
Well, so I mean, in the quantum mechanical view, a photon is detected with a probability that is determined by the amplitude of the electromagnetic wave at that point, right? And so, moving the lens around, moving the lens around doesn't really have any effect. The electromagnetic intensity at a given point will still be whatever that is. Of course, if there's something there, the probability of interacting does depend on the ability to interact. There has to be something for it to deposit its energy. I'm sorry, I'm getting kind of bollocksed up because I don't really understand. You
Well,
always bring these
I
scenarios that
bring
are
this scenario from a manufacturing
strangely
side
complicated. Yeah.
because they're how you manufacture, and so these are the stories that come from manufacturing. The guy can't polish the lens to anything better than at the point where the way that the atoms align in lattices
Okay.
end up
Okay. So you really
changing
are
the
talking about an imperfect lens. That's fine. So go ahead.
well, sure, imperfect, or even the lattice structure ends up having a different zone of acceptance. So if you change the orientation of the lattice structure, you have a different acceptance.
I also don't understand this zone of acceptance thing. What do you mean by that?
Um, is it going to bounce off or is it going to go into the
How
lens?
is that a zone of acceptance? I'm not sure. I mean, I just don't understand what you.
Or
It's
I
like
think
when
he
you
means
cut a
angle. He
diamond.
means angle of it. He means angle of acceptance.
sure, angle of acceptance.
Are you talking about an optical system or just a lens?
Yes,
You had an aperture. You were talking about an aperture at the
sure.
beginning.
So my point is, the aperture is after it goes through the lens.
So you're
So
talking.
if you
So
change the
okay, just
probability that it gets into the lens, the
let's just
aperture sees a
understand the
different
system.
probability.
You're talking about a situation where you have a lens, and then behind the lens you put a barrier that has an aperture in it that some of the light
Mm-hmm.
coming out of the lens goes through.
Mm-hmm.
Okay. Okay.
And so if you change the orientation of the lens, that will change whether or not the aperture receives or does not receive a signal.
Yeah, sure. Whether or not it's an imperfect lens, right? A perfect lens would do that.
Let's say it's perfect down to the atomic structure, but the lattice of that atomic structure has a acceptance angle or a
Well, see,
refractive
that's what I
angle.
don't. I don't understand the acceptance angle of the atomic structure. What is that referring to? I don't understand what that means.
It's kind of like polarizing. You have a polarization at which it may go in or it reflects or refracts.
Okay, I just don't understand the verbiage. The acceptance angle of the atomic structure. I just don't. I don't.
Polarization of the latticing of atoms. No?
Now,
Okay.
I just don't follow, Joe. It's a common failing. I feel like you have something in your mind that you're not telling us enough about for me to at least follow. If somebody else does, maybe they can jump in.
Well, I think what Joe is trying to express is that if you have a molecular structure and a photon, that when the photon meets the molecular structure, certain interactions are possible. It could reflect, it could be absorbed, and it could travel through, it could be refracted. And
Yeah.
which of those things it does depends on how the photon hits it, how much energy it has, where on the molecular structure it strikes, if it strikes on the corner, if it strikes on the flat. All of these things are determinative of which of those outcomes happens.
Well, okay, so fair enough. I mean, the point is that if the lens is not has imperfections, has atomic structure, then yeah, I mean that's one lens is going to do something different than another does because it's a different lens.
But I think more
If you're going to try to
precisely,
describe that in
these are
terms of where a photon strikes, you're doing something other than you need to have a model for how that works because that's not the way quantum mechanics views it, the thing that we
well, I
actually
think
do
that's right. But
calculations,
I think that that is
because
one
it's
common complaint about, and this is
so
the complaint that T. Hooft would offer, is that quantum mechanics just doesn't
Before
describe.
before you go to Hoofs,
Let me just try to understand what Joe's what he has in mind. So Joe, are you saying? I mean, there are a lot of things going on. I mean, it's kind of a little bit confusing. So you have a light source, right? Point light source, and then you have a aperture, a slit, right? And then in between, are you putting a lens? Is that what you're
Yes.
trying to say? Okay.
Mm-hmm.
So, and then the lens is in the path, in the straight line path of the light source and the slit, right?
Yes.
Okay. And then you're trying to orient the lens, turning the lens around. Is that what you're trying to say? Or
Let's just say that it hits the same exact point on the lens,
no? Okay.
but you change the orientation of where the lens, of how the grab a telescope, a binocular, right. Imagine you standing with it right in front of your eye. You have to change where your body position is, but
No,
in order to get
just
the light to
before
hit the
you
exact same point on the
invoke anything
lens.
else, before you invoke anything else, all right? So let's do it one step at a time, all right? So you have instead of a lens, okay, and then we go from the simplest thing, okay? Instead of a lens, instead of a convex or concave lens, we have a planar glass, right? Glass plate with
Right.
certain thickness, right? And it's a
Love it.
plane and parallel plane, right? Okay, and first we insert the glass plate between the source and the slit, and then let's say the plate is parallel to the wall of the slit, right? And then the light goes through the glass without any refraction, right? And so that's the original position, right? Do you agree with that? Or
Yeah, let's go with it. That's
okay,
great. Nice
all right.
flat surface. Love
Now,
this as an experiment.
cool. And then now we put a axis, rotational axis, through the plate, so we can rotate, right? So what do you want to do? Do you want to make the plates originally planar plate into a convex or concave lens, or you want to rotate the plate? What are you thinking?
I think the easiest one might be just rotate the plate, and let's just agree that the structure of atoms might be different
Okay, before we
between
go into atoms,
between the
because
plate
there are a
and
lot of
the aperture.
things, right? Going down to the scale. First of all, you have a planar plate. That means your wavelength is actually larger than the atomic, let's say the lattice distance, right? And then you have, so that's well, we're in the realm of geometric optics, or you can shrink the wavelength to smaller than the
Ooh.
lattice spacing of the atomic structure. So which one are you thinking?
Well, I don't want to take you down that parallel. That'd be terrible. Um,
Let
it's
me
a
try
good.
something. Hold on a sec, Joe.
I'm trying to
Hanson,
understand
I like
because
what you've done.
Joe, I mean,
Let me.
there are a lot of things. You can have diffraction, the Bragg diffraction, and if your wavelength is small, but you don't have that when the wavelength is large. So what realm, what regime are you thinking about?
So can I just try here, Hanson? I think what you said is valuable. The idea of having this plate that you then are just rotate, right? And in the rotation, because glass is made of atoms, and they won't be exact. The plate will be different when you've rotated it. It will be different. There's no question about that. And then the question is, what difference does that make? As you've pointed out, because light has a large wavelength compared to atomic structure, it shouldn't make much difference if the atoms are arranged a little bit differently, but it will make some difference. And I certainly agree with that. But I think the important thing is that the difference would be calculated by talking about what happens to the wave and then asking about what the wave looks like further on. If you want to talk about ultimately
Well,
detection, you have to let that wave pass through the entire glass, and you have to use all of the contributions from that wave to determine the probability of actually ultimately detecting a
There we
photon
go.
somewhere. If you want
So
to say the photon hits a particular place on the glass, you're just not doing physics. That's not the way it works.
in between the deterministic state of whether or not, let's say you have a star and you're trying to determine if a planet goes in front of it or not, in that data collection process, this is one of the educations I got, is that the angle of that lens and down to the atomic structure ends up changing your ability to say whether or not you were able to positively take that information or negatively interpret that information, or you didn't get to collect it because it diffracted.
Well, but I think you're just
And so the
talking about
atomic structure ended up becoming,
resolution limits of optical devices that come from lots of scenarios. First of all, you need to make your mirrors as correctly as you can, your lenses as correctly as you can. You want to make your
anytime that
apertures
you
as
have
big as
a
possible.
lens, then you have a resolution.
Right. You do, even if it's perfect, you have a resolution limit because
I feel like
because
we're
of aperture, Rayleigh's criteria.
I feel like we're sort of talking about a kaleidoscope on a much smaller scale
Why do you say that?
because the way that you rotate the parts
Oh,
of the instrument are going to influence how you see the the end results,
well,
even though nothing is changing on the other side.
yeah, kaleidoscope is kind of, I mean, it's kind of a macroscopic. It's not, small scale imperfections. It's
Yeah,
really large
it's
scale
scaled down.
movements of mirrors. Yeah. Yeah. Well, anyway, I mean, I think the key thing, Joe, for me is just that you want to have some kind of a model where if the photon hits this part of the lens, then it will travel in a different direction. But you just there you need to come up with that's not the way
I was told that
physics
was
would
the
calculate it.
limitations of the lens when being manufactured, that became game that's what they were getting down to. So they
Sure,
couldn't
and
make the
that's
lens better
true.
than that. And
Right.
that was
But
becoming problematic, was down to that.
but it's not because of where a photon hits. It's just that if the lens isn't perfect, the wave after the lens, which is going to determine where photons do ultimately get detected,
Well,
is
no,
going to
they got
be,
it perfect. They
distorted.
basically proved as much as they could that the damn lens was perfect, and they were trying to figure out why they still had not as much. They were going to predictable objects, and they weren't getting responses where they expected them.
A resolution kind of a problem, you mean?
Yeah.
Yeah. Well, I don't know about that. It strikes me, I mean, it's hard for me to imagine. Uh, well, no, it's not hard for me to imagine. You can always calculate, of course, the how well you can grind a mirror, right? What the how many wavelengths you're willing to tolerate, or what fraction of a wavelength you're willing to tolerate in the out of sphericity, or whatever it is you're trying to grind the thing to. And that's one determiner, but then aperture is another thing. Aperture is usually the limiting factor in optical systems in terms of resolution. But I can imagine situations in which it's the ability to grind the mirror. I don't know. Maybe we should. This is a place where we need Bert. Bert would be a perfect resource here. He knows this stuff. But anyway, I think Benjamin would have it be a little bit different, and would have, for instance, in the case of the single slit that we just talked about, he would have these be really literal photons that go through the slit in a definite place, maybe hit the edge, maybe tumble off of it, maybe have their little football points tumbling. And that's fine. You can come up with a model like that, but somehow the model has to be able to explain why you get the pattern that quantum mechanics says you get.
This fun fact brought to you from Kitt Peak National
Have you got
Observatory
a link?
in, well, that's kind of where the lens got used. So it was a Kitt Peak in Arizona, I believe, is where that lens got ultimately used. And that was
May,
somehow where the resolution at a Earth-based observatory.
well, if you have a link to the thing you're talking about, I would take a look at that.
Is anyone else familiar with structural color
Not
in
me.
biology? In biology,
Oh, I'm
so
not familiar with anything in biology, so that's a
so
me
that
problem.
that's
Electron phases on an atom, giving different colorations, and as well as infrared
No,
wavelength
I think he's
variations.
talking about the diffraction.
I'm talking about the way that certain species of hummingbirds have iridescent blue feathers, but that is due to the way that
Ah,
the
interference kinds of things.
the
Yeah.
way that the feathers are structured so that they
Yeah,
reflect
diffraction.
certain wavelengths of light.
Nanometers
Diffraction.
of light.
Okay. Diffraction.
That's a good parallel to this.
Uh-huh. Well, it's an interference phenomenon,
You have
right?
the same exact, I guess, light hits the same spot on a feather, but you change the make and model of the feather.
Well, I mean, this is just diffraction. If you put a soap membrane on a piece of glass and then put it on the sunlight, and then you move the soap foam membrane of foam around, you see different colors.
Oil
That's
floating
diffraction.
on water,
Yeah,
thin film interference
thin
kinds of
film,
things.
oil, thin film. It's the same thing.
Yeah, but I do think, I mean, Benjamin, what you were talking about, I mean, I think really is, it's the central thing that you talk about all the time. But I think the problem is, as I say, I don't know, do you conceive, do you imagine that somehow with your ideas you can make these photons fall on the screen the way they do, the way quantum mechanics says they
So
will?
I think that T Hooft gets into this, right? And T Hooft does not provide a model that would do this at the level of the real.
At the level of
But
what?
the real,
The real?
as opposed to the merely statistical. So if we
I see. Oh, I
statistically
see. Okay.
say, if we throw photons through this hole, statistically they'll come up and give the diagrams that you're going to provide, right? And we have a model for that, and you can draw these little diagrams, and then you can say that the statistics add up, which is if you take a bunch of things that have, statistically 35% probability, and another set of things that have a negative 35% probability, you add them together, you get zero. And that statistical addition is workable, but T. Hooft is saying, yes, it is, but it also doesn't describe reality. And that a theory of reality would describe what happens to a single photon going through the slit, and it would tell you where it's going to go based on its initial conditions. And if you run the same initial conditions, you'll get the photon land in the same spot.
See, one of the weird things with when we go to the double slit, probably next week, we'll see that a double slit pattern is really just a modulated single slit pattern. If the two slits are relatively small and close together, they both produce the same single slit pattern. If you block either one of them, you'll just get the pattern that we talked about today. But when you open up the other one, photons never land at many places where they do land. If you have both slits open, if you have only one slit open, you get photons landing everywhere in that central maximum. Whereas the moment you open the second slit, photons never land at many places within that central maximum.
Well, that's a good example when you change the light of each one, where the zone of both of them are overlapping, you get a different perceived effect.
I didn't understand that.
Well, actually, the
I don't like
double.
that particular segue where we make a claim and then we follow it. Well, that claim is like another claim. The claim needs to be addressed directly.
What's the claim that needs to be addressed?
That there's some places where the photon doesn't fall. First of all, I'd say I doubt that that's truly the case, but I
Oh,
suspect that it is the case with a single frequency of light. You change the frequency of light, and I'll bet you no longer have that situation.
well, no, you have that situation with any frequency of light, but the places are
Any
different.
single frequency of light, right? But if you have a plurality of frequencies of light, then I think you'll find that all of the spectrum is all of the space behind the system is gets some light somewhere.
Well, that's true, but I don't know how that solves your problem. Your problem is that if you shine a laser on a double slit, and you start with one slit closed, you get a single slit diffraction pattern. And the moment you open up the second one, a lot of the places where light was falling before are places where no light ever falls.
Yeah, so it is interesting, but as we move this photon through the double slits, let's say 80% of it goes through one slit, but some portion of it has to kind of drift off into the other slit.
Are
Now,
you
that
saying this because
portion,
you're aiming the laser more at one slit, or you're just proposing that for
yeah,
some?
let's
Okay,
no, let's
that,
suppose. I mean, you try your best to get the laser
yeah,
wherever, and it
and
goes
that's always the
everywhere,
case, right? You never get
and
it
that's always
exactly
the
right.
case.
Yeah.
There's photons coming out all kinds of ways. A fire hose of photons, right? Even if it's a very quiet fire hose, they're coming out at all kinds of angles, with all kinds of speeds, I might add.
Well, but the important
Uh,
thing is you can never aim the laser so that it illuminates both slits identically.
okay. Um, but one photon anyway is going to go, somewhere down, right down the middle or off to the side. I don't know what. If that photon is absorbed or reflected,
By
it
what?
has to be absorbed, well, by the apparatus. Certainly, a lot of photons are going to get,
By the barrier, you mean that the
yeah,
apertures
the
are? Yeah.
barrier, right?
Okay.
A lot of photons are going to be, let's say, reflected and or absorbed. I don't know what the barrier is made of, but if it's made of charcoal, probably they get absorbed. In any case, things are going to happen, but there is this quantum reality, which is if it's absorbed, it kind of needs to be absorbed in whole because the thing that
It,
absorbs it needs either a whole photon or it doesn't know what to do with a half photon.
that's
So
right.
I think that as it goes through and makes a mess of this thing, it the edges there, the little parts, have to decide whether they're going to catch the ball or reflect the ball or dodge it. But if they don't collect it or reflect it, then the fact that it gets kind of separated for the moment, the ones that we see go through kind of have to piece themselves back together on the other side of this on this wire. And because it's just energy, I don't have a real problem with that energy going through on the other side of the wire and then collapsing back down and forming up the basic idea of an electromagnetic self-oscillatory system.
Well, the
So
only
that
problem that
node,
I have is just, I mean, there's a lot of like, I don't see how you could, well, it could be like this, it could be like, I mean, come up with a model. I just think that the problem you've got is that it's easy. You can do it yourself. You can go out and buy a cheap laser. You can
I
draw,
have
you can
done it
take a razor
myself.
blade, you can do these slits. And what you will see is that if you shine that laser on two slits and you cover one up, you're going to get light in a lot of places where it does not fall the moment you open the
Well,
second one up.
can
That's
can I
weird.
put
And you
two
have to be
slits
able
and
to
I
explain
divide
that.
the space of the two slits with two different lasers and give them different wavelengths?
Mm.
Okay, you can do that, and then you'll get two single slit diffraction patterns with different colors, right? They won't
But
interfere because they
John,
don't have a.
why do you think that this is not susceptible to a deterministic explanation?
Well, I didn't go quite that far. I'm willing to accept. I think it's possible that there is some kind of a deterministic, thing. But whatever it is, it's got to. It can't be just little footballs. Either bouncing off. If footballs going through one slit sometimes fall in a place and stop falling in that place the moment you open another, you give them another way to get there. That's weird. You have to be able to explain that.
Well, I just think that it's not a football in the sense of something that once you cut it in half, it stays in half. I think it's a kind of like a piece of fire, if you will. And
It's
if
like
you
a
chop a,
wave.
if you, no, well, yes, it is like, but not a statistical wave of the kind you imagine, right? I think it's engaged in an oscillatory phenomena.
Well,
And I
I
think
think
too often
you should. I think you should.
waves,
You and
waves are,
Tehuft should put your model together, and or
but you,
Penrose. And
yeah, well, I hear you. That's fair. But people, I'll give you a video of one of these guys saying that the wave is not real. It's just a description of statistics.
yeah, I think that's fair too. I think we have no direct measurement of a wave. All we can do is measure photons, measure interactions, right? Whenever a wave interacts,
Right.
whenever a light wave anyway interacts with something, it does so in the form of photons. That's what a photon is an interaction
So,
between an
see, here's the thing
electromagnetic
with the
wave.
with the slit is that I think you and I can basically agree that at least there might be a deterministic explanation of this phenomena. And we don't have any Bell theorem that's going to insist that we sort out our differences. And so I'm not sure that you can really properly form the major conflict in quantum mechanics with just the dual slit experiment. I've tried, but
Yeah,
I don't think we can get there.
well, I think I agree. I don't think there's a Bell-like theorem that rules out coming up with some kind of a deterministic way to do the double slit. But of course, there is the fact that that Bell's theorem says correctly that quantum mechanics makes predictions that can't be explained by a local reality.
I just think that when you hit this thing and you hit a double slit, that whatever part of it has to go through the double slit is going to go farther. It's going to take longer. It's going to slow it down, and it's going to kind of bend it or
Well, when you say
or
something goes through it, how does something go through a double slit?
well, if a photon is made of electrical potential and magnetic potential in alteration, then we're talking about the localized field going through the double slits. Obviously, the
Well,
material of the double slit.
if it's localized, it can't go through double slits. It goes through one or the other.
Well, clearly, I think that that interpretation will fail.
Well, I think so too. because I mean,
But
I think we've shown that it fails.
how big can a photon get if it's a magnetic
What does
field
that
and an
mean? I mean, it's not
electron?
a
How
photon.
big?
This is when I enjoy microwaves and how you don't cause yourself radiation. And so it's the wavelength and at
I mean,
the
it's true. You could look at a
Right.
microwave as long as you're looking through 1/8-inch holes. The energy can't get through an 1/8-inch hole, and that's because the microwave is bigger than an 1/8-inch hole. And I think light is much smaller than that, but it is still of a size. But that's the size that blocks like 100% of the energy.
and
How?
honestly, that 1/8 inch hole is kind of what I was talking about lattice. And let's say it's not an 1/8 inch hole; it's a 1/7 inch hole, but now you change the orientation of it so at which the acceptable uh, hole size is essentially an 8 inch. Follow?
Yeah, well, I think so, Joe. You're talking about microwaves, right? Radio in general, things on the low side of infrared start having such small, low energy photons that we never
Things
talk
traveling at
about.
the speed of light.
Well, everything, yeah, they all travel at the speed of light, but the difference
Cool.
is that below infrared, you're talking about photons that have such low energy
You know what would be
that
an
we don't
interesting
detect
experiment,
single photons.
John, is that when we do this experiment, we most often do it with a single frequency of light and a detector that's sensitive to that frequency of light. And visual spectrum is pretty narrow. But if photons go through and get chopped up, there may be some photons that get cut in half and they end up with like half the wavelength. They may end up off frequency. I wonder if we could find them.
You
Well,
mean
I
like
mean, you do
something doing
know.
phase angle firing? The difference between like
Well,
AC
there's
zero
only so many
crossfire and
things
phase
light
angle
can. There's only
fire.
so many things a photon can do when it encounters a barrier like this. It can
How
be
about this? Ooh,
reflected.
let me do this. Let me take an AC
It
wave, okay?
can it can be transmitted without alteration. It can be uh, affected. It can be transmitted or reflected with some alteration, and it can be absorbed. Those are the only things it can be. Now, if it can be any of those things in part, and we think that it must do some things in part, for example, it must do transmission in part because it gets bent. And so it's not perfectly transmitted. It could be reflected. Possibly it could be reflected in a diffractive way, such that there's the similar pattern on the reflected side. I don't know that anybody's looked for that. But what we haven't discussed is whether it could be partially absorbed or split into two particles that have half the energy, and that would be interesting to look for.
I do this in power with AC power in how to create a excitation in lamps. So you're using infrared lamps to heat in a vacuum because you can't use a heating element in a vacuum because there's nothing to conduct the heat. So you need to heat a circuit board, but how are you going to heat it? You have to use infrared light in order to warm it up. And so the way that you modulate how much temperature you're getting out of where you desire the heat to be received, you you can do something called phase angle firing, which is that you're stopping where in the phase the power is applied to create the excitation in infrared light.
Certainly, I know what phase angle firing is. I think Ben might even know what phase angle
So,
firing
so
is, but
basically, I
I
mean,
don't
I
think
think
it's
what you're
relevant.
saying is basically is the same as a diffraction, same as the wavelength, and you have different in the time. You, you stagger the time of excitation of the source so that it and goes in the same in the
Did,
particular direction. It's the same kind of interference pattern, just like the phase array radar. It's the same principle.
What have I missed, guys?
Hey Ben, oh, we're just trying to do a full accounting on the double on the single slit experiment. Where does the energy go? There's recently been an experiment that looked at this. Did you see that, John?
I'm sorry, I'm
They did
distracted
this
by something.
experiment with a very careful strain gauge on the slit to see if they could measure the amount of force that the photon puts on the slit in order to deflect, because obviously the photon can't deflect right unless it puts some force on the unless something deflects left. Conservation of energy. But to answer your question,
Momentum.
Ben,
Momentum, yeah. Jinx there, John.
the question still remains: what are all the possible outcomes for those photons, and are any of them split in half? And that would be interesting to look up. And I don't know that anybody's ever looked for them.
Well, I mean, there is, down conversion, right? I mean, you know about that from
Yeah, yeah.
entanglement things, right? So you can do that kind of thing. But it does, photons don't, as far as we know, split just by themselves. It's an interaction, an absorption, and then a re-emission kind of a thing.
Right. So without the absorption and readmission, there's no down conversion.
I think so. I mean, I won't swear to it, but I don't think there's any process in which a photon spontaneously converts to two low energy photons.
How about this? I do like the no, that's the density of gas. So the aurora, when you do get a sunspot, ends up changing the colors based on the atmosphere elevation because the chemical makeup of the atmosphere ends up being different. So you
Right.
get different excitations in electrons.
Right.
And so
Aurora in general,
and
they're
so the
colored
time of the
differently at
night
different
ends up
altitudes.
changing the colors because the zone of the Earth being in the way of that region of atmosphere changes whether or not those zones are exciting.
Just hold on a sec. I gotta go for a sec. I'll be right back.
Yeah, no talking bullshit while he's gone, guys.
Ben, how you been? I've got
Talking,
a test
talking.
coming up. 2
We want
days.
talking. We want talking. Just not. Oh, somebody's ringing. It's John. I'll mute him. There you go.
John is
You got
calling
a
you?
test. Yeah, but let's keep on the topic for now, just of the bite of physics and the double slit, because we'll be back in a minute, and we don't want it to go off the rails just because John's disappeared. So what did I miss? I was away for a while because I was having dinner and doing family things. But what's the gist of what I missed? Because now I'm pissed.
That if you add up all the angles of all the contributing components of a multi-slit diffraction grating kind of experiment, you get different angles at different positions, and if you add them all up, sometimes they null. They create a full circle. They come back to point A, and those are the positions where no light is detected.
Okay, yeah, I think that was part of the presentation. Okay, thanks, buddy.
Yeah. And now we're just trying to explore those parts of this topic that deal with particle versus wave, or wave versus like statistical wave versus a real wave. The stuff that Tehuft is on to. I don't know if you're familiar with Tehuft. Are you
No,
paying
not by
Tehuft
name.
any attention?
No, I mean, I
So he's a
just my
Nobel Prize winner who is saying that if we had the real mechanics of how light works, we wouldn't be stuck with these models that merely describe statistical models that merely describe statistically what's going on are inferior to models that describe actually what's going on, the kind of predictions that can models at least that can in 3 dimensions maybe represent what a photon is doing.
well,
And go ahead.
yeah, I mean, for a given photon, things become statistical, but you don't need too many of them before the emergent behavior becomes completely predictable. So I'm personally not too worried about that.
Yeah. Well, you're not worried about this field in general, so I guess that wouldn't be a surprise, I guess.
What's to worry about?
Yeah. Not keeping me up at night.
Yeah.
Well,
Well, I mean,
that it doesn't keep you up at night because you turn the lights off and the lights go off properly because people understand how this shit works.
Do they though? Do they really?
no, it's the thing is, Benjamin, I think you're going to have a hard time making progress because unlike Penrose and Teheuft and other people, you don't want to start by throwing out quantum mechanics, right? I mean, those guys don't deny the fact that quantum mechanics makes correct predictions. That's really
Well,
the problem that you're in is you have to come up
you
with a
know that
theory
Penrose says
that
as
makes
soon as there's
right
mass
predictions.
displacement, the predictions of quantum mechanics fall apart. So
Well, I
um,
mean, so once
it's
again, I
not
mean,
that
just to
married to
just
the
to
notion.
just to prevent the descent into dishonesty here, Penrose
Oh
doesn't.
boy.
There's no prediction of quantum mechanics that's been experimentally verified where Penrose thinks that prediction is wrong and the experimenters are lying to us. That just doesn't happen.
He certainly doesn't use the term lying. I'll
Or that
concede
they're
on that
or that
point.
they're mistaken. There's no experiment in which he thinks no prediction of quantum mechanics that experimenters that has been well demonstrated that Penrose thinks was wrongly demonstrated or that was wrong itself. Right, the predictions he has, he takes no issue with any of that.
I think that he is firing a bazooka at the whole thing when he says it's totally wrong.
Well, he is, of course, when he says
And
that. That's nothing but a bazooka. But he also is being. I mean, I think you can tell from the fact that he acknowledges that the polite thing is to say incomplete. He's acknowledging that that's really what he's saying. He just doesn't like saying that. He likes saying it's wrong. And I'm kind of in that camp, right? I mean, I like saying that Newtonian mechanics and gravitation is wrong. It is, and I defend that. It is wrong. It's not incomplete. It's wrong. But that doesn't mean that I or anybody else who thinks that the predictions of Newtonian mechanics that have been verified were wrongly verified.
yeah, I mean, I guess you can have your cake and eat it too. I don't see how it can be completely, totally wrong, according to Roger Penrose. And all of the experiments are excellent, verified,
Well, well, I just gave you a good
necessary.
example. I think Newtonian mechanics is totally wrong. And I think that with very minor exceptions, we've never done anything other than what was done before Newtonian mechanics, and that is to verify the, the vast majority of predictions of Newtonian mechanics to the precision that we're able to. Most of the prediction in our daily lives, in engineering kinds of applications, you can't detect the amount by which Newtonian mechanics is wrong. It is wrong, but you can't detect it. In the vast majority of cases, that wrongness is too small to detect.
Mm. Well, I think you and Roger have a conversation you need to have.
It'd be a
Reynolds
shame to.
really enjoyed.
Sorry. I was just going to say, it'd be a shame to lose the wood for the trees here. It was a good presentation on how diffraction works. If people listening took that to heart, you can do a lot with it, predict a lot with it, build a lot with it. It'd be a shame to. So, the Kahneman's peak end theory is that you remember the best part of an experience and the end of an experience. If you're going to end it on
Mm.
Benjamin's quantum conspiracies, then that kind of potentially will compete for the peak, which was John's beautiful physics presentation. And we might not then go off and build cool shit with what we've just learned. Just my 2 cents.
Well, thank you, Ben. And I think maybe I will, on that note, maybe bring this to a close. If somebody wants to, of course, well, Benjamin will have a room. I'm sure we can continue there. I'm going to go and have some breakfast. But I did want to say that I do intend to continue this, probably do double slits next week. I want to talk about triple slits, quintuple slits, 10 slits, and ultimately, thousands of slits, because it's really nice. First of all, the phaser approach that I've introduced here, now that it's been introduced, we can really tear through all sorts of other things. And I think you'll enjoy what happens when we talk about double slits and then more multiple slits and then ultimately what are called diffraction gratings. How diffraction gratings are the final result of having effectively an infinite number of slits. And all of that stuff is accessible very quickly once we have the phaser thing under our belts, and we can even say at least a few approximate things about Rayleigh's criterion, which maybe we'll end the whole thing with. So that's what we'll do next week. And unless somebody has, a nice kind word to say about physics, then
Oh
we
boy.
won't we won't go down. I think Ben is right. We'll end this on a high
So
note.
there's an interesting thing about diffraction gratings, which is they can be used to separate frequencies and then make a spectrograph.
That's right.
That's
That's
pretty
right. And in
cool.
fact, are the best kind of lab spectrometers
Are
are
they?
based on diffraction gratings. Yep.
Yeah, that's pretty cool.
Yeah. Yeah. No, that's good. So we
Favorite
will
just
we'll
uses a
definitely do that.
spinning disk to create that filter.
To create a diffraction grating like thing, is that what you're saying? A
Yep.
high speed.
All they do is it's a glorified rotating disc in front of the lens. So you put a rotating disc in front of the lens, and that's what then allows you to pick up on various infrared chemical breakdowns. So you get the nanometer of that chemical differently than another chemical based on their infrared signals.
Is
There
is
has to
is
be
this?
something, and I'd like to know. There has to be something about that disk. It can't just be
Yeah, I was going to say,
a
It's
is it?
spinning at
uniform
a
disk.
certain RPM.
But what but
Wow,
It's
what
okay.
what is the
no, it's the
property?
aperture as a whole. You got a whole
Hmm.
aperture in the spinning disk, and now the rest of the disk is a plate. So there's no light going through. So you're
Oh,
filtering
so it's not
out
a
the
it has
nanometers.
nothing to do with a spinning disk. It's chopping the light. Is that what you're saying?
Yes, it's chopping the
Yeah.
light before it comes
Yeah. It's a
Chopping
into
the
the
light
light.
lens.
chopper. It's not a spin. I mean,
Yep.
it's a light
And
chopper
then they
built to
Chopping
spin.
can.
the.
See, this is like, I mean, it's just a word of advice, Joe. You say things like spinning disk. Uh-oh. When
Spinning
it's not
aperture.
the spinning disk that's doing anything, right? Yeah.
Well, what is it that's doing the work here?
Oh shoot, let me get rid
What
of
is he
that.
talking about?
There we go.
What is
I'm
he
still
So,
on
not sure
about?
what he's
okay.
talking about, frankly,
Here,
but
you have lead fillings in your teeth, and you go get cremated at the hospital. The hospital needs
As
to
one does.
environmentally comply that they didn't put too much lead into the atmosphere. So they have to record how much lead gets put into the atmosphere, and this is one of the ways at which they do it. Is they detect during their burns how much gas flow and essentially the infrared decay on the things going out of the incinerator, and they use a lens going to an aperture, and in front of that lens is a plate with a hole in it, and when you rotate that plate with a hole in it, a disc essentially with a hole in it, it creates a filtering effect of which light can come in. And so you're cutting different nanometer wavelengths that are permitted within to the lens and
So,
aperture.
John, how are you cutting the? How does that work? Can you explain that? What he's talking about?
oh, well, I
To
think
build one of
it's
these
just
things,
like
what was
this is like a Fitzo apparatus. Fitzo measuring the speed of light by passing light through basically a fan blade, right? I mean, it's not even an
Yeah,
aperture. It's really just radial slits that alternately let light through and don't let light through. And I'm reading about it here. I didn't know about this
in this
technique,
case,
but
it would
it's
be a single slit. It's not a dual slit. It's not a fan
well,
blade everywhere. It's the purpose is to make sure that you have resolution
well,
by.
but I don't think it needs to be a. I mean, you can have a rotating disc with many radial slits in it. You're just trying to chop the light, right? It's not. Isn't that the point? You're just
Yeah, the
trying
point
to
is to
turn it
yeah,
into
chop the light.
pulses. You're trying to turn it into pulses. It's
Only
not important
accept
that there only be
certain
one per
pulses versus
rotation.
other pulses.
Well, I don't know. That's a little too vague for me to wrap my mind
You're
around. But
you have two wavelengths of light that might be coming in, but you only
hmm
want to receive one.
Well, so if you're suggesting that this chopping doesn't let one through, now
Yes.
I guess I'm skeptical of how that would work. But
Well, if you just want to split the different wavelength, you use Bragg diffractor,
right,
the diffraction.
That's just a diffraction, right?
Exactly. I mean
And
that
you could
the
rotate that in front of a camera or a sensor, and you get something.
yeah, I mean
But what are we doing with
the different
what are we
wavelength
doing with these discs?
will be scattered off in different directions.
No, nobody knows what we're doing with it last time, I
You
guess.
you tune each rotation per chemical band that you're looking for. So you change the
but what
rotation
do you?
per chemical band.
But what is that? I don't understand. This doesn't make any sense. I mean, it's not like you're
This is
not.
hardware. It exists. You can't say it doesn't exist. It's used.
Well,
Joe,
the
can I give you
It's not the
advice?
hardware that doesn't make
Can
sense.
you
I'll take it.
when you say something, can you like researchers and put it in kind of precise form? It's just like it seems like you're just like seeing something and then put it everything jumbled into one bin and then pour it out onto the table. It's like a I don't know. It's just too jumbled.
Yeah, and you can't. I mean, the thing you can't do. It sounds like you have this idea that somehow by rotating this thing at optical frequencies, you're just letting the peaks of one, like, what is it, 10 to the 14th
Optical
cycles per
frequencies?
second?
You think this
Well,
thing is rotating at
no,
optical
I don't. But I
frequencies?
think this is Joe's conception of it, is that it's letting the peaks of one frequency through because the little aperture comes around every time a peak of one frequency comes around, and then blocks others because it doesn't come around when the peaks of that one come around. But that would require rotation frequencies of like 10 to the 14th, 10 to the 15th
That's not
cycles per
what's
second.
happening here. This
Well,
is
I know it's
just
not what's happening, but I do kind of
one
get the sense
sample
that
per
that's what Joe suggests
rotation.
is
You're
happening.
getting a blank sample. You're
Right.
getting a baseline, and then you're getting a value, you're getting a baseline, and then you're getting a value.
I'm
I
reading
don't
I
about
think
know.
this
John nailed it.
process.
I just
Uh,
gave you the product inside chat.
it's a NDIR. Is that it?
NDIR is
What
very
is it?
common, yes. That's
Yeah,
an
is that what you're talking
IR.
about? Is NDIR? I don't know anything about that, but it's,
Yeah, NDIR is going to be used for measuring infrared and identifying gases in the sample. If you have a
In this
carbon
case, the
monoxide detector or something like
so
that,
here.
it's
So
probably
here's
going to
what
be
here's
nitrous
what my
oxide is a big
AI
one.
says. An NDIR gas analyzer. The process involves an IR source, infrared light source emitting a beam, a rapidly rotating thin plate with a bow tie or segmented shape that interrupts the beam at a constant high rate, a gas cell. The chopped light passes through a sample cell containing the gas flow. The target gas absorbs specific IR wavelengths characteristic of its molecular structure. Detection: a detector or multiple detectors with specific filters measure the amount of IR light that passes through the gas cell. The concentration of the gas is inversely proportional to the amount of absorbed light. Blah blah blah. I'm still not quite sure why it has to be chopped. It doesn't.
So one
But
of
it's
the key
certainly not
elements of
chopping it in order
NDIR,
to,
So
you
you
need
don't get a photon signal from the carbon monoxide signal versus from the nitrogen signal. You want to differentiate the two, and that's why you're chopping the photons, the infrared light emitted off of both of them, because one of them will have a very narrow nanometer band.
and a way to say this is you have a control and you have a sample, and you want to keep your sample and your control separate. Maybe the chopper is doing that work. Some of them just use two detectors. If they're solid state, they just have two detectors. But if you chop, then you can use the same detector, and that gives you like better resolution because the same detector is going to have the same sensitivity curve.
well,
I don't quite follow it.
I'm gonna look for a
Look,
better.
it's probably
Yeah,
to improve. It's probably to do something like improve the signal to noise ratio of the measurement or something. It's probably
that's what
nothing to
Yeah.
do with fundamentally being able to make the measurement
I think.
downstream.
That's
You
right. I
could
think
make
it's
it with
like
a
a lock-in
continuous beam.
amplifier or something. Kind of a.
It's like to classify that one element is different from another, that this nanometer band of light intensity is only received from that molecule, not the other.
Well, but we already knew that, right? I mean, I think Ben
Yeah, but
is right.
you
Is
could
that
you So you could whatever's doing the detection. If you chop the incoming light at a given frequency, you can now use this as a filter. You can say ignore any signals where they're not being chopped at however many hertz, and by doing that, you can improve your signal to noise ratio. You're basically just
Hmm.
coding the light. You're just coding the light signal. When we bounced lasers off the moon at the local university, we didn't just bounce a beam off and hope for any beam coming back. You put a digital signal. You put some hex characters in the beam, so that you know that what comes back is what you sent. It's just a question of improving signal to noise, I think.
Yeah, I think it really is like a lock-in amplifier or something. Then you can look for signal at that frequency and know that it's the signal you're looking for.
It's an interesting bit of equipment. Thanks for sharing it, Joe. The only thing we were contending from a physics point of view is that the spinning is necessary, absolutely fundamentally necessary for the discrimination. The discrimination is being done by the looks of it by simple filters. The point is the spinning
Remember that one room that you? It was
gives you a way
like
of
2 years
improving the
ago.
mechanism.
2 years ago, you had a topic about spin,
Me?
and this, yeah, 2 years
Oh,
ago,
did
you
I?
were talking about the physics of spin at
Was
some
it?
point,
Okay.
and this instrument has been stuck in my mind ever since.
Mm. But I don't
I,
think
I
the
ju-
spin is relevant here. I think it's just a way of closing off an aperture and opening it rapidly.
yeah, I think that's right. It's just chopping the light. I mean, it's just a mechanism, a simple mechanism to chop the light. I see lots of people kind of talking about this in the chat, and I feel bad. I mean, of course, they could raise their hand and come up on stage and tell us if they wanted to, and I'll give maybe a few moments for that. But I do want to shut this room down. This is an interesting thing, though. I do want to find something that explains. Oh, Io, you're here. Did you know something about it?
Yeah, yeah. So all the rotating wheel does is you can have different filters, but it just converts a DC measurement into a narrow band AC measurement. That's like the fundamental concept. So, yeah.
What did he say?
So when you say a narrow, it does sound like you're talking about lock-in kinds of things. So the
Exactly.
detector, yeah,
Exactly.
right, yeah,
It does
Yeah,
what
you
now
you you
exactly?
hit you hit on it with the lock-in amplifier. So
yeah,
it just creates synchronous detection. So
right.
then you have a reference signal and so on. So yeah, it's pretty
Yeah,
cool.
and then you can improve the signal to noise and get better readings. I think we've bottomed it out.
Synchronous
Ben,
detection.
if you wanted if
Weirdly,
you
the
do
one
start
thing
another,
it precludes is synchronous detection, but okay.
Yeah. Okay. So good enough. Thanks, everybody. We will see you next week for the double slit, hopefully. And be careful on the clubhouse streets, I guess. Let's see, what have we got? Oh, I'm just going to do this one. Yeah. All right.